When you look at the world around you, it seems like just a mess, right? You've got waves, wind, sand, all this complex life. But what's incredible is that the whole point of physics, its fundamental goal, is actually super simple. It's all about finding just a handful of basic rules that explain, well, everything. So let's dive in and try to figure out the rules of this game. So, a lot of physicists have this great analogy for what they do. Imagine you're watching a grand game of chess, but it's being played by, I don't know, nature itself. And here's the catch. You have no idea what the rules are, you can't ask anybody. All you can do is sit there and watch the moves being made, and from that, you have to try and guess the rules of the game. In this cosmic chess match, the board is space and time, the pieces are the fundamental particles, and the rules? Well, those are the forces that tell the pieces how they can move. So how does physics actually make progress? Well, there's this key idea called amalgamation, and really it's just a fancy word for unification. It's this amazing process of taking two things that seem totally separate, like, say, heat and motion, or even electricity and light, and then realizing, wait a minute, these aren't different things at all. They're just different faces of the same underlying reality. It's all about finding out how the different puzzle pieces connect to form a bigger picture. Okay, so let's jump in our time machine and go back a bit. Before the 1920s, physicists felt like they were on the verge of winning this whole game. Seriously. They thought they had it almost all figured out. This was the era of classical physics, and man, the rules they'd uncovered seemed so elegant, so complete. It looked like the game was almost over. And in that classical world, the universe felt, well, pretty straightforward. The stage was just simple, three-dimensional space. And time? Time just ticked along, separately, like a big, reliable clock for the whole universe. The players on this stage were the 92 different kinds of atoms, and they moved in really predictable ways. They were just being pushed and pulled around by only two forces we knew about: gravity and those short-range forces we call chemistry. But hiding just beneath the surface of that neat, tidy picture was a force of almost unimaginable power. I mean, think about this number: 3 million tons. What on earth could that be referring to? Believe it or not, that's the force that would exist between two tiny grains of sand. We're talking just a millimeter across if you put them about 30 meters apart, if their electrical charges weren't perfectly balanced. It turns out that force of chemistry we talked about, it's really just electricity, and it is ridiculously, monumentally powerful. The only reason the world doesn't fly apart is because it's almost always perfectly canceled out between positive and negative charges. It's a giant on a perfectly balanced leash. Now, figuring this out led to a massive breakthrough in how we thought about forces. The old idea was, that one charge just kind of magically pulls on another one from a distance. But it turns out that's not what's happening at all. Instead, a charge creates this condition in the space all around it. We call it a field. And if you jiggle that charge, you send waves rippling out through that field, exactly like dropping a pebble in a pond. And that's why it takes time for the force to get from one place to another. And this idea of the field? Oh man, this was a huge moment of amalgamation. It connected so many dots. It revealed that radio waves, radar, the visible light you're seeing with right now, and even X-rays, they are all literally the exact same thing. They're all just waves rippling through this one electromagnetic field. The only thing that makes them different is how fast they wiggle, their frequency. So things are looking pretty good, right? We're unifying forces. It feels like we're getting close to the end. But just when we thought we were about to checkmate the universe, everything changed. After 1920, the quantum revolution kicked off, and physicists suddenly realized the game they were playing was way, way stranger than anyone could have possibly imagined. I mean, the entire classical worldview was just completely shattered, gone. That predictable clockwork motion, out the window. Solid little particles? Well, it turns out they also act like waves. Space and time being separate? Nope, they're fused together. That neat and tidy universe was replaced by something that was uncertain, based on probability, and just deeply, deeply weird. But for all its weirdness, quantum mechanics immediately started solving problems that classical physics was totally stuck on. Here's a big one. You've got a positive nucleus and a negative electron. They're attracted to each other, right? So why doesn't the electron just spiral straight into the nucleus and the whole atom collapses? Why are atoms stable at all? Well, the answer is one of the brand new, mind-bending rules of the quantum game, the uncertainty principle. Think about it. If an electron actually fell all the way into the nucleus, we would know its position with almost perfect precision, right? It's right there. But the uncertainty principle says there's a trade-off. The more you know its position, the less you can know about its momentum. So by being confined to that tiny nucleus, its momentum becomes wildly uncertain, giving it a huge kick of energy, enough to blast it right back out. It's this beautiful quantum compromise that keeps atoms from collapsing. And this new reality had another shocking consequence. It was the end of a predictable future. You can have an atom that's all ready to emit a particle of light, and you can know everything there is to know about it, but you can never, ever predict exactly when it's going to do it. At its deepest level, it seems nature is just playing a game of dice. All we can ever know are the odds, the statistical averages, not what's going to happen next for any single atom. Okay, so the rules are bizarre, right? It all sounds crazy. But here's the thing. Once we started to understand these new rules, mastering them led to one of the absolute greatest triumphs in the history of human thought. We started to get really, really good at playing this quantum game. And that triumph has a name: quantum electrodynamics, or QED for short. This is the theory of how light and matter interact, but with all the new quantum rules baked in. And I'm not exaggerating when I say that to this day, it is the single most successful, most precise theory we have in all of physics, period. I mean, the power of QED is just staggering. You feed it just two numbers that we measure from experiments, the mass of the electron and its charge. That's it. And from just those two inputs, the theory correctly predicts pretty much all of chemistry and all of electricity. It explains why a neon sign glows the color it does, how dense salt is, everything. It even predicted the existence of antimatter before anyone had ever seen it. It's just incredible. So with QED, we have pretty much total mastery over everything happening outside the atomic nucleus. We've got that part of the board figured out. But the moment we try to peek inside the nucleus, oh boy, the game gets messy all over again. And that is the frontier of physics today. So physicists were trying to figure out what glues the nucleus together, right? What holds all those positive protons together when they should be repelling each other. They called it the strong force. A physicist named Yukawa came up with a theory and predicted a specific new particle, a meson, that should be the glue. And guess what? They went looking for it in cosmic rays, and they found a particle with the exact right mass. It looked like a home run, but it wasn't the right particle. It had nothing to do with the nuclear force. It was the first clue that things were about to get really chaotic. And that discovery just opened the floodgates. All of a sudden, we weren't dealing with a few simple chess pieces anymore. We had a whole particle zoo on our hands. Dozens and dozens of new, unexpected particles started showing up. We had all these new pieces on the board, and we had no idea what their rules were. But just like before, out of all that chaos, a new, deeper kind of simplicity started to appear. It looks like, despite this whole zoo of different particles, all of their interactions, every move they make in this crazy game, are governed by just four fundamental forces, four basic rules of interaction, each with a vastly different strength. And that really brings us right up to today. We've kind of pieced together the edges of this giant cosmic puzzle. We've got the big picture stuff like gravity, and thanks to QED, we've got the world outside the atom's nucleus pretty much nailed. But the center of the puzzle, the heart of the nucleus, that whole particle zoo, it's still a jumble of pieces that we're desperately trying to make fit. This grand amalgamation of nature, it's been an incredible human triumph, but it's also a beautifully unfinished task. You could say we've figured out the rules for how the pawns and the bishops move on the board, but the game is so far from over. And the big question, the thing that gets physicists out of bed in the morning, is still this. What strange, and probably even weirder, new rules govern the game at the very, very heart of reality?